Still making that noise, isn't it? Turn all microphones off. I can still hear the hits. Brilliant. Okay, so excuse me, I'm sorry guys. So I want to start with two photos. I can't see them. You put them up. One by Ken Beck. Programs have two kinds of value. What they can do for you today and what they can do for you tomorrow. And by Edmund Burke, considerably earlier, society is indeed a contract. It becomes a partnership not only between those who are living, but between those who are living, those who are dead, and those who are yet to be born. So Kent Beck is talking about programs, and Edmund Burke's talking about society. And he was writing this in response to the revolution that happened in France. And Edmund Burke, as you may or may not know, is essentially the father of conservatism, and is certainly the he was both a liberal and a conservative. So I thought I'd tell you a little bit about what it means to be a liberal and a conservative, and then we'll see how that relates to what Kent Beck is talking about. In the political system, a conservative, well, here's a massive oversimplification, tends to be someone who, well, there's all sorts of definitions as to what a conservative is, but if we take the current Liberal Party of Australia's definition, because there's been a bit of debate about this recently, they've published their books and so on. A conservative is someone who isn't against change, but likes change to happen in small steps. Rather than big sudden change, like revolutions and things like that, a series of gradual, slow changes. Because we've got something that works, let's not monkey around with it too much, let's make a series of small progressive changes to move to the next state, rather than a big sudden jump. And a liberal is someone who believes in the power of the individual and individual autonomy, who thinks that people should have as much choice as possible in society, should be as much as possible masters of their own destiny, controlling what they do themselves, and have as little interference from the government, the state and so on. And these two different ideas are often opposing political ideas, but in Australia, and a little bit worldwide, they were united in the Cold War by a common fear of socialism, communism and the Labor Party. So the Liberals and the Conservatives joined together and formed what is now known as the Liberal Party of Australia. Now, can I say I like both these ideas? I like the idea of change happening slowly, step by step. I think that's really good. If you've got something good, you don't want to break it, do you? Unless it's terribly, terribly, terribly wrong. I guess civil disobedience is okay then. But basically, work with what you've got and make slow changes, that's good. But I also like the idea of individual autonomy. I think individuals should have as much choice as possible and look after themselves as much as possible and be in control of themselves as much as possible. Now, with programs, we sort of want the same things. We want to build a system that works, and once we've got a system that works, we don't want to do massive changes to it and muck everything up. We're nervous about breaking it, because it's so hard to get the damn thing to work. We're really scared about breaking it. And similarly, with programs, we've discovered through painful trial and error that programs where the individual components of the programs have autonomy and look after themselves tend to be more robust and better programs than programs in which programs have the individual components, the units of the program, controlled by some master like God, tyrant object that's telling everyone exactly what to do. So let's just reflect a little bit on that. Why does it often turn out to be that giving the components of a program autonomy leads to a better overall program? You guys tell me. Well, I haven't even defined what it means to be a better overall program, so better that soon, but maybe that'll come out of your answer. Why do you think we like this idea? You've hopefully seen it now a lot in Java, of giving objects more control, more say, more interfering with them as little as possible, letting them look after their own destiny, their own specialisation. You look after your problems, you look after your problems, you specialise on your problems, and interacting together will produce a wonderful, beautiful system, rather than you telling every single one of those three guys what to do. Yeah?
I guess it's because when they're all sort of working by themselves, you don't actually, like, once they work, you don't really need to do anything with them, you can just use them, rather than if you have it all controlled by one thing.
Yes.
Usually when you change the program, you're changing the big thing that controls it, so then something might go wrong and then you can't just use the object because it's something you might have changed what the object does.
That's a perfect answer. Did everyone hear that? I was listening, waiting to hear one key word. And then you said it, and then you kept saying it. It was just making me happier every time you said it. What was that key word? Change. Change. If you write a program and nothing ever changes, it doesn't matter whether you write it in machine code or binary or your monkeys type it out on typewriters, whether it's in Assembler or Java, whether it's a God object or everyone's got control of themselves, all of that sort of stuff. Who cares? You've got a program that works, it solves the problem, everything's okay. But, unfortunately, that sort of situation is not the sort of situation we really ever write programs for. And let me draw the picture that I always draw. I sort of want to skip one. A little icon. I have another iconic picture, but we're not going to see that probably for a couple more weeks. It's called the Q stack. But, well, that can be a surprise for you when it appears. But the iconic picture that, for me, symbolises this whole course, drawing very carefully. We've got a problem, we've got a solution, hopefully, that's what we want. And the traditional design thing is going from problem to solution. But what we're interested in is the fact that the problem comes from some guys, girls, people generate the problem, tell us the problem, ask us to solve the problem. This comes from people. And the solution is programmed and designed by people, teams of people. And the solution is used by people, or has an impact on people in some way. Or, being devil's advocate, maybe a program that has no people using it? Maybe something on the Voyager that's travelling on space, but I guess it communicates back with us, but after it stopped communicating back with us, I guess it's like the fridge light, who cares? Like a rover? I don't know. Let's just pretend it's always for people. It's in some context anyway, it's a solution to something. Certainly these are the two main ones we're interested in, because most problems, the people that tell you the problem, this is us, okay? We're writing the solution. The solution is usually a program or a bit of software or several bits of software, interconnected systems surrounding that. We write this knowing full well that even if we've understood the problem correctly and implemented it correctly, these guys didn't state it properly. And whatever we give them, they're going to come back and say we didn't like it. Or we're going to give them, they're going to like it, but then when it's used by the people, these people are going to complain to these people saying it's no good, it's not what they want, and they don't want to use it or something like that. So the initial understanding of the problem is unlikely to be the real problem we need to solve. And furthermore, even in the miraculous case where we get that right, very, very soon after, they're going to change it. They're going to say, oh, we want it to be Web 2.1. We want it to be in HTML. We want it to be on the internet. We want it to be 3D. All movies are going to be 3D from now on. We want it to be, what else? What other changes? Multiplayer. We want it to use a mouse. Or just whatever program you write, the environment in which the solution is operating and the requirements of the people writing is going to change. They're going to say, can you do it in different currencies? Can you allow credit card payments? Can you have a rollback feature? Can you allow voting? Can you put the time in the top corner of the screen? They're just going to keep adding things to it. So the software we write now is for what we can do today. But actually, and this is a traditional approach to software. Yeah, this is what I was taught when I was your age. Gather your requirements, go through an enormous month or year-long process speaking to the end users, and speaking to the people generating the problem, find out what they really want, then go away and think about it for a year, and then produce hundreds of tables and diagrams, and then write thousands of lines of code, and then at the end, 3 years later, give them the solution. And that was what software engineering was. And it was all about how do you measure what they want, and how do you turn it into formulas, and how do you automate the generation of the code, and how do you make sure that what you're producing matches exactly the original specification. They were the issues of software engineering back then. But right now we know that's sort of more or less, it's not irrelevant, but that's not where the system's going to fail. Even if we manage to solve all those problems, we don't understand the problem, no one understands the problem, the problem's going to change something. So the traditional idea is you do the design up front, then you implement it. And then what actually happens in practice is things change over time. People add CRUDs and patches to the programs and try and make it do these extra features. And over time, the program degrades and the beautifulness of the program gets worse and worse and yuppier and yuppier. And then eventually it's just this awful, disgusting mess. So that's... Because when you're writing a program, the last thing I guess I sort of want to say about that is when you're writing a program, your boss may well not be interested in what's going to happen tomorrow. Your boss may well only care about what's going to happen today. And if you say, well, I'm setting up like this so that it can be adapted to future changes and things like that. The boss comes, I don't care, we haven't got those changes here now. Just get it to solve these problems. And in a way, that's fair enough. That's what we've talked about with agile development. We don't want to support extra features that we haven't been asked to support. That's madness. But what we do want to do is write code that's well designed and beautiful. And by well designed and beautiful, we mean it will turn out to be easy to modify. It's not going to fall into pieces as soon as someone changes the problem. And if everything explodes into complexity or falls into pieces when the problem changes, even a little bit, we call that brittleness. We say it's a brittle solution. We don't want a brittle solution, we want an agile solution. One where, when they make the changes, that they will, like I've told you in the first week that you've probably forgotten, I'm going to change the spec of the assignment twice during the assignment period. If you've got a brittle solution, it's going to just be so annoying. In the final exam, I'm going to give you your assignment code, and the prac exam is going to be, oh, the assignment spec's changed, fix it up. Once you've got your code working, you can leave the exam. That's your final practical exam, just dealing with the spec change. So if your code, because I did that because I didn't just want to be standing here talking all the time and blathering on about it, and you believing me because I'm convincing or because I'm loud or because there's hypnotic, some sonic sound playing or something like that. Because that's moronic, isn't it? Yeah, that's what we learned in 1927. You don't believe anything anyone says. You certainly don't believe anything I say, because it could be wrong. It's probably wrong. I'm a very, very forgetful person. In fact, did I tell you in 1927 I told you some deliberately wrong things? Did I ever reveal that? I did. I had this great joy when I was talking about skepticism to tell you several things that were deliberately wrong, some of which people spotted. And the annoying thing was often as I was doing the wrong thing, someone would call out, that's wrong, and I'd go, oh, okay, and I'd change it. But I managed to slip two things through that no one ever corrected. They're about the complexity of certain modifications of insertion sort. And I told you that, I explained how they worked. I'd already told you how to calculate complexity, but then I gave you the wrong formula. I said, so you can see the complexity of it is this. And those were questions in the exam. And I was proud to see that most people got it right. So either you just didn't pay any attention at all, or if you did, you didn't memorise the facts, you worked out. Because you can't believe anything I say, because even if I'm not maliciously, deliberately misleading, I'm probably accidentally misleading you, or I might even think it's true. In the old days, they used to think there was an ether, and the atom was a plum pudding, and they used to believe all that, and telling you that wouldn't have been ridiculous. That would have been university education, and you would have got a tick for it in the exam. But things will change. So you can't believe anything. So this is why I'm doing this. My plan is now you will know in your heart what it means. Because if you write, you really have an incentive now to write code that when I change the spec, it's not going to be hard for you to change your solution. And there's no faffing about and talking and waving hands. Well, there is, I'm doing it now. But you'll see when you write your code, you'll think, yep, okay. And if he changes it, so whatever, changes it in this way, I only have to change this class or these two classes. That's a really good solution. If it's, I suggest a change and you have to change every class and throw everything away. That's a bad solution. That's a brittle solution. So programming for tomorrow means not that you put extra features in now. Yeah, that's a waste of time. No one wants to. But you write your code in such a way. You could write it this way, or you could write it that way. We're indifferent between the two in terms of correctness. But one of them is going to be flexible and nimble for tomorrow, and one's not. And because of this change thing that underlies all that's, I guess, going to cause us nightmares in software engineering and programming, adapting with change, we're going to prefer this solution heaps more. Now let's look at what Burke says. Society is indeed a contract. It's a partnership not only between those who are living, but between those who are living, those who are dead, and those who are yet unborn. And actually, I think that's quite a profound thing to say, except those that are dead people. I think the conservatives pay a little bit too much attention to dead people. I only believe in worrying about the living and the future ones. That's called the fallacy of entrapment, to worry about what's happening. But this notion that society is a contract, so if you, I don't know, get a nuclear waste dump, and you put it up in somewhere in the Northern Territory, and you pay the current owners of the land $100 million, $100 million, then they're going to get $100 million and be completely happy. But that waste dump's going to be there for 100 million years. So that's $1 a year you're paying to everyone. But the first people there are going to get it all. Yeah. And they're not really caring so much about the future ones. Yeah. This is it. So society is sort of about that. It's about caring about the future ones as well as the current ones. And that's what our program is going to be like. Now I've got a program to show you. What I want to, I put this book in. Each week I'm trying to cover a different book. I'm going for a beautiful book. This is Refactoring by Martin Fowler. Martin Fowler's an awesome guy, and this is sort of the thing that broke refactoring onto the scene. It was in the 90s. It's quite an old book now, but it's still very, very, very beautiful. I'm going to go through his first worked example in this lecture today. We'll just look at some of the refactoring stuff. It's a book well worth getting hold of. It's an awesome book. So our idea is not going to be do design up front, have a perfect design it for 3 years, then code it for 2 years, then it's released. Our idea is instead going to be this notion of incremental design. So we're going to add our features in one at a time, and every time we add a feature, we're going to add it in a possibly messy way, just to get it correct and get all our unit tests passing. And then once we've got all our, because we need tests, yeah, because when you change from one design to another, I did it the other way around. When you change from one design to another, and remember I said we're sort of indifferent between which one we have for the external reasons in terms of correctness, but this is better in terms of future flexibility. When you go from one to another, you do really want to be indifferent between correctness. You want to make sure that this is correct and this is correct. There's no point going from one design to another and this is more beautiful, but it's wrong. So this is our whole idea of unit testing. We build up these great banks of automated tests, and then we rewrite our program to be more beautiful, but hopefully it's a correctness-preserving rewrite because we run our tests on it again and we're not happy till those tests pass. So our plan is we do a dirty rewrite just to get the new test to pass. And then we're left with some dirty code with the extra functionality, but we only had a little bit of functionality at the time. Yeah, it's just a small change, it's conservative. And then we're going to rewrite our code, rechange it, refactor it to make it beautiful again. So today we're going to go through a slow step-by-step refactoring. But you get the idea, it all happens in baby steps, small steps. We don't add all our features and then refactor everything. You can't do that, it's a nightmare. And we don't design everything up front. Well, that's exactly what I said. Designing everything up front and then implementing it, that's adding all your features and then doing the factory. It's too hard to do that. So we just do it slowly. Okay, let's look at his first example because it's really cool. I've pasted the code up here, but pretty soon we'll flip over to the Java picture. I had this idea, we sort of do it like a puzzle. I'd show you the code, and you'd start to think about, let's turn some lights off. I want you to sort of think about the changes you'd make to make the code better. So that's it. This is code about a video library, because I had those back then. Where you could get movies, and you could rent them for some period of time, and it had customers, and the customers occasionally got a bill saying how much they had to pay. And this is going to keep track of which movies you rented, and how long you rented them for. And depending on what type of movie it is, it'll cost a different amount of money, and then they'll print some sort of invoice or statement at the end saying how much you paid or how much you have to pay, depending on how they work out. Okay, so they're going to have 3 classes, is the original design we're starting with. We've got a movie class, one per movie. We're going to have 1 object per movie. We're going to have a rental class, 1 object per rental. So that's, a rental is going to involve a movie and a period of time. And a movie is going to involve the title of the movie and also what sort of movie it is. Is it a new release or a kids movie or a something else movie? And they'll all presumably cost different amounts and have different prices. Okay, we have children's new release and regular. He's storing it just as a code, 3 different codes to represent 3 different types. So there's our movie. The movie just stores the title of the movie and it stores the price code. This variables, he starts with an underscore so you can spot that they're attributes. They're private. So to access them, people are going to have to use what? Getters and setters. Okay. And does the constructor use a getter and a setter? Or a setter? What does the constructor do? It writes to the field directly, doesn't use a getter and a setter. But okay. But anyone else in the outside world wanting to access this is going to have to use a getter. There's a getter for get price code. There's a setter for set price code. And there's a getter for get the title. And presumably they don't ever want to change the title of the movie, but they might want to change the price code because maybe it was a children's movie once. Oh no. No. Maybe it was a regular one and then become a new release. So they might want to change it. Right, so we've got our movies. Just absorb that. We're going to follow this whole example the whole way through. I don't know how long it'll take us. It might be time consuming. But at least you won't have to learn things over and over again. Pay attention now because we're going to see these classes for the next half hour. Then we're going to have a rental class. That's going to store 2 fields. It does store 2 fields. A movie, which is the movie that's rented, and then for how long it's been rented, which is an integer. It's got a constructor, and it's got getters, no setters. So you just create some record of a rental and it never changes. Presumably, might think about how you do this in practice. Presumably you create this record after they've returned it. A little bit of retrospective billing system, a novel way of doing video recording. Because you can't change the number of days, and they've got customs like maybe they'll get late. Alright, so it's got to be the number of days that have to be already. Alright, so that's our second class. They're both simple classes. Does everyone get both those classes? Notice accessors and constructors are public, and the attributes are private. Our last one is the customer. That's going to use an enumeration and a vector. Well, actually, I'm hoping in the second lecture today we'll have time to look at vectors and more generally the collection class. Java's got these built-in classes for storing objects. So everything we did in 1927 was about, well, a lot of them were about dictionary structures, weren't they? So we could have we looked at hash tables and binary trees and skip lists. Did we do skip lists? Trees, queues, stacks, sorted lists, unsorted lists, sorted binary trees, all these different things that you can shove items in and then query the structure to get the item back or find out if it's in there or not. Yep. They're called collections, all those sorts of things. Well, Java has examples of those already coded for you, which is really nice. So from now on, you'll never have to write one yourself unless you're doing something crazy that people in Java have never thought of. You can just use Java.collections. And there was that joke about that in the interview I read last time about that guy who sorted in one line by calling collections.sort. So they're data structures and the associated algorithms with them. So default ones that are sensibly coded are already available for you. So let's have a look. So an enumeration, enumerations are, no, we'll get to that later. We now do, Java's changed a bit since then. So we'll look at iterators today. Okay, an enumeration is just a way of getting every object in a collection. Give me all the objects. So let's have a look at the customer class. The customer has a name. A customer has some rentals, which is a vector, which is a collection, which is a, well, I don't know if a vector really is a collection because it's before the collection class, but it's something you can shove a lot of things into, and it'll remember them. It's like a list or something like that. It's got a constructor. When you create the customer, you store their name. You've got a get name function. Do they have a set name function? No, so customers can't change their name. Well, that's not a very good design straight away. You've got something to add a rental. So once they've returned the video, you add the rental to the system. This is a video shop I need to go to actually. Really good. You never return it, perhaps they never add the rental. Okay. Well, and then they've got this little function here to print out a statement. And if you want to look at it, you'll see it prints out rental record 4, the name of the person, and then it skips through all the rentals that they've had. So as long as it has more elements, as long as there are more rentals that are there, it'll scan through them all one at a time. It's calling each rental each, so it rips them off. Get the next rental, convert it to a rental, and sort of each. Inside the loop, we're going to process each one. Depending, each rental will get its movie. From the movie, we'll look up the price code. Based on whether it's a regular, new release, or children's, we'll increase amount by 2. What's amount used for? Let's have a look. Where's amount used? Total amount. This amount. Oh, it's adding up to money. Okay, all these amounts are being added up to work out how much the total cost. So this amount. So this amount is the amount for this movie, I guess. And at the end of the loop, you must add this amount in. Can anyone see where this amount is incremented? Ah, here we are. The total amount has this amount added into it. So the total amount is slowly built up. And presumably total amount is initialized to 0. Yep. So this just scans through all your rentals, adding up how much they all cost. It also, depending on how many days you rented it, I know the cost depends on the number of days. I saw something else. Oh yeah, down here. If you've got a new release, everyone gets a frequent renter points every time they rent. Looks like it increases by 1. And if the movie's a new release, and each day's rent, for every day you rent a new release, you get an extra frequent renter point. Woohoo! So you can get lots of frequent renter. That's like free rent. Okay, and then at the end of calculating, looping around, adding up all your frequent renter points and the total cost of all the movies, it prints it out. Result equals tab, the title of the movie, tabs, the amount of the movie, prints out for each one, and at the end, in the footer, it adds to result which is a string you're building up slowly. The amount you owe is this, and you earn this many frequent renter points. Notice, by the way, this is very annoying to look at because it's very wide, isn't it? It's going up the screen. Does anyone notice we've been fooling around with the style guide. The style guide's all very experimental at the moment. Someone requested we increase the width of the style guide. So we've done that. Well, as an experiment. We've said you can go up to 80 characters wide. What was it before? 76? But if you really need to, you can go up to 90. We're saying keep it under 80 as a rule, but someone was saying in some special cases it's really, really important to be able to go wider than 80. So in extreme emergencies where you think it's really important to go up to 90, we'll have that rule for a while and see how that goes. But already I'm not liking it because look at the width of these lines. It's very annoying because you lose the end. There you go. All right. So that's our design for the video library. You've seen those classes. Does anyone have any comments? We've now got, it's actually not a very good design. It would be a fine design in C. No, it wouldn't be a good design in C. But it'd be okay design in C. It's not very good for Java. We're now going to make it a better design, slowly, step by step. So let's have some suggestions for how to improve it, but only in baby steps. What's the thing looking at? What things, you've probably seen a couple looking at, instantly stand out and make you think, ooh, that doesn't look right, that's a smell.
It's full of magic numbers.
It's full of magic numbers. Thank you. Absolutely. That's a sting. Yes?
All the calculations taken care of inside the customer class.
All the calculations are done inside the customer class. What's the problem with that?
Customer class would probably just be a customer and you might have another class taking care of calculate rental fees.
Okay, so there's nothing that obviously says calculations of rental amounts belongs in customer. Is that what you're saying? There's no obvious thing for putting it there. Maybe it belongs in its own class or something like that. It has to go somewhere. What's the problem with putting it there? 1010, yeah. Let's just look at this. Beautiful small class. Beautiful small functions, 2 lines, 1 line, 1 line, 1 line. Beautiful small class, 2 lines, 1 line. Beautiful small class. Oh my God! Look at this. That is what we call a smell. What's going on? So yes, absolutely, there is some problem with that method. It is way too long. So, yep, did you have some?
I don't know.
All right, so what we're going to do is, well, what do you think our first refactoring step's going to be? What would you do? Guys, you've got to make a change. I'm going to say, you've got 5 minutes. So you haven't got time to rewrite everything. Pick the one thing you're going to change. What would you change? Because we're going to do our refactorings one step at a time, and after doing each refactoring, what are we going to do? Run the test. We're not going to change too much in one go. Yeah?
Let each movie know how much it costs.
Let each movie know how much it costs is a beautiful objective. It's actually going to take us a while to get there, that's right. We haven't got this decentralized thing we want. The movies don't know how much they cost at the moment. That information is sort of distributed around a bit. Maybe and it seems a lot of the magic numbers that have this information stored. Who was talking about magic numbers? Yeah, a lot of the magic numbers that store this information about how much movies cost seem to be in the customer class, which is, as you pointed out, really crazy. But it's going to take us a while to get, so let's do something simple first. We'll get there slowly. Because that's a big change. What are you going to do? Well, one of the tutors, tutors, which tutors have we got here? Is it only you two guys at the back? Are there any other tutors? Right, who wants to be Liam? He's not here, it's okay. All right, Jackson, you're Liam. Okay, Liam, up the back. Yes, Liam, what would you do? What would you tell your tutor? You're marking this piece of code. You say to the student, it's not so good, perhaps you could.
Well, take that switch statement into a separate function. And
Yeah, pull this out. What's it doing there? So, whenever you have a really long method, break it into multiple methods. Because that method's doing too many things. This method's formatting an output string to print out the results, but also doing a whole lot of calculations as well, doing too many things. So when you've got a method that's doing too many things, we don't like it. We want each method doing one thing. So we'll take that chunk, and I reckon that's a good chunk to pull out. We'll pull that out, and we'll put it in a separate method, still in this function, but then this method the statement method can call that calculation method. And now the calculation method looks after the calculation, and the statement method is still doing some calculations, but its clarity is increasing, and certainly the current is. Okay, we're going to call that extract method. So that's our first refactoring technique. When you've got a method that's too big, pull some methods out, split them into little ones. That's called extract method. And Eclipse even has a tool called extract method that if you highlight the method you want to extract and click on extract method, Eclipse will rip it out, sink it down the bottom and change everything for you to make it all work. So you don't even have to do this manual stuff. Now let's flip over to the book and we'll start going through multiple rewrites. Well done, Lee. Now, if you've not been getting enough sleep, this might appear a bit blurry. And that's a good indication to get more sleep. Here's the old version. As big as we can. He's done in bold the thing that's about to change. He's picked the switch statement too. That is a big ugly switch statement, so he's going to pull it out. Let's now look at. I have the clarity this is going to be okay. It's looking pretty hopeless, isn't it? Can everyone read that? What about light in terms of contrast? Does it contrast enough? What would help? More light on this, or Google Docs, yeah. Or less light in the room, maybe? Well, let's send you to sleep. Is that better? Yes. Yes, okay. It's just you and me. Is that too dark now? I'm going to try this for 5 minutes, but if everyone seems to be falling asleep, I'm going to change. Okay, so that's the old one. Now what he's done is he's ripped it out, here we are, and had it into a separate function called amount for. So all that calculation was just to update this amount. So now he's put it all into a function called amount for, and where's amount for? It's down the bottom here. He's written amount for. There's a separate function down the bottom. It's got the switch statement in it. Everything looks the same. He's had to initialize, done the initialization inside here, and he returns this local variable for this amount at the bottom. And that does all the counts. Is that cool? So I had to create one more local variable. Good. Hasn't reduced the overall size of the class, but it's reduced the method size. That's a good one. Okay? Now, what's the next magic step? I've got a little cheat sheet here, which says all the steps he went through. Yes. What's happened is you've seen this ugly piece of code, this initial ugly piece of code. You've seen it because you've been called in to work on it, and you've been called in to work on it because the people who maintain the video store have told you they're going with the internet, and they would like to have code that can produce statements in HTML as well as the old text-based statements. So you've just got to kind of flip through the code and you thought, oh no, I have to write HTML statement generator. That's going to be awful and ugly. Why is it going to be awful and ugly to write an HTML statement generator?
The output's all embedded with that other code.
That's exactly right. Is it Dave?
Yeah.
Yeah. That's exactly right. The calculation interleaved with the output of the other statement function, and that's really dependent on the physical structure of that old output. So you would have essentially, naively, if you were going to write this new thing, you'd have to write a new, equally long, disgusting thing with the calculations intermingled in the code to duplicate that one to do the HTML codes. And then we'd have duplicate code. Why do we hate duplicate code as well as making us read more? What do we hate about duplication? It's hard to debug? Yes, in what way?
So if you change one, the other needs to...
Yes! Yes! It's more likely to get bugs. Yeah. If someone then decides, oh, we're going to change the way we calculate the cost of the movies, they might update one of the functions and not the other. You've now got the calculations happening twice. The calculations happening in two different spots. They're not synchronized in any way that the language knows about. If you're going to monkey around with one of them, you have to remember to monkey around with the other one. And maybe you will and maybe you won't. They're all in the same huge ugly class, so they're near each other, so you might notice the other one needs to be changed. But what if there were 10 different ways of printing out statements, or 20? Or you know, people started thinking of ways of doing it remotely at other sites and in other files. And, the idea is we want every bit of responsibility, every bit of calc to be just done once in one spot. So if something changes, we have to change one thing rather than changing lots of things. So that already freaks us out. So while we're sitting there absorbing that, they say, oh, and by the way, we currently have new releases, kids' movies and regular rentals. But we're thinking of introducing some new movie types. And we don't know what sort they'll be yet, but we'll probably change the billing for all the types when we do that. And we'll probably change the way we calculate it. And you're starting to think, oh no, so now they're going to have lots of different movie types. That's going to change. And you think, these guys, I know what's going to happen. In 6 months, they're going to change it again. And you're looking at the code, and it's depressing you. Even though it's correct now, you realise the cost of change is very high. So your plan is, you're going to refactor the code to make it beautiful, and then when these changes come along, it'll be easy to do. Because at the moment, it's very, very hard to change this to produce an HTML statement. But after we've refactored to make it beautiful, as it should have been done up front, it will be very, very easy to add an HTML statement. And at the moment, it would be very hard to add new movie types, or it wouldn't work out very well. It would be very hard to add them nicely. But in the future, it will be very, very easy to do so once we've done the refactor. Okay, so let's look what happens next. He fools around with the code a little bit and does some renaming of variables because they've all got disgusting names that aren't very clear. We can skip over that and go to page 16. All right. I don't want you to read the clue at the top, and I brought in some tape for this purpose. This is my high-tech approach. Oh, it didn't work. It's transparent tape. Well, there you go. How smart. All right. There's something. This is what it looks like at the moment. Is the bit that we've extracted. It's the amount for function, the case that we returned. He looks at it and he notices something strange about it. Something that's alarming. And this is something that someone's already indicated. What data does this method operate on? This method's in customer, but what data is it operating on? Rental. It does rental get a movie, and it looks at movie, a constant from the movie class, movie not regular, and then it looks at a rental dot get days rented, and the result is the cost is a rental gets days rented again, and it gets from a rental it gets days rented again, and from a rental it gets days rented again. It doesn't actually access anything from the customer class. It's only accessing data from the rental class and a little bit of data from the movie class. So that's a strong indication of what? It's in the wrong spot. Your methods should be really obsessed with their data. Remember, we want this idea of, we want things to be coherent. We want, inside our class, everything to be all related. So the data that the class stores is all related to itself, and they're sort of integral. You could pull any one of them out without sort of destroying the integrity of the class. And the methods are all really to do with that data. In other words, the class isn't just a brand, like when I pack the car, when we go on a trip, here's how I pack the car. I get everything I need and I throw it, it's a ute, I throw it in the back of the ute. It's very messy. It's not a good way of packing. But I just think it's a container and I'll shove everything in there. But when my wife packs a car, it's all very systematic and she puts things in labelled boxes and things like that. Well, I'm a bad OO car packer. Because we don't want our classes to be just everything shoved in randomly, willy-nilly, because we've got to put them somewhere, so let's just stick them in the closest class to hand. We instead want everything to be where it makes sense for it to be. So we don't like this method where it is. It shouldn't be there. So what are we going to do? Yeah, we're going to move it. And this is called move method, our second refactoring technique. We've seen second refactoring technique. We've seen extract method, and now we've seen move method. Well, we haven't seen it, but we're about to. So how are we going to move it? Well, it's very, very easy. Like this. There we are. He moves it over to rental. I'll use my little pencil pointer. Now, the switch statement calls the getMovie function of the current rental. If we look still at the constant from the movie class, and getDaysRented is now our local function. It's our getter, yeah, for our attribute. There's rented. Yep, it's all looking good. Much simpler. And now it's using data where it belongs. So that's really cool. Okay, so we've now done a move method. Now, page 20. Skip a couple of boring refactorings. Oh, and I won't use tape, I'll use clipping. Alright, he reaches everything works, he's very, very happy. He's going back to the statement and he's looking at something and he's not completely happy with something. I'm going to point with this big one. He's looking at this code and there's something now a bit yucky. The clue is it's got something to do with around here. What's happening to this amount? What do we notice about this amount? It's the one, that's the place where we stored the method we moved. What any thoughts? What's that? Say it again. What if each points to null? Oh yeah. That's a good question, and that's arising because I haven't, this is coming from the fact that it's an enumeration, or we're going to call it an iterator. The enumeration does this magic thing where the enumeration's been accessed in a couple of spots. It's created up here. We ourselves won't be using enumeration. It's created up here called rentals. And it says, go to the rentals vector, remember there was a vector called rentals, and give me all the elements from that and put them in something called an enumeration, which I'll call rentals. So I've got rentals now, which is essentially a list of all the elements that are in the thing. And then I can use this built-in, because rentals is an enumeration, it has a function called has more elements. And as long as there are elements in this list, that'll be true. But as soon as the list is empty, it'll be false. And that list is a list of enumeration. There's a list of rental elements. Actually, yeah, you're right. Actually, sorry, I'm talking rubbish. None of that protects this from being null. It could be null, couldn't it? Because a rental could be null. But that's sort of the integrity of our system, that hopefully we've never stored a null rental. But yeah, that's right. It could be null. The enumeration would store nulls, presumably along with legitimate rentals. Yeah, because, yeah. So it could be a list and some of them are nulls. But let's hope that our system makes sense, and overall no one's stored any nulls in the system. But there's a sort of an ickiness about this as well, which is, when you're looking at this amount and working out how it's used, what did you have to do? How long did it take you to work out how it's used? Could you just see straight away what it's used for, what it's needed, what it's doing in the program? You couldn't, because it's too far from where it's used. Yeah, it's used down here. Only used here and one other spot. Here, here and here. It's only used here and here. It's used at the top as well. Oh yeah, it's declared at the top. Then it's initialized here. It's used down here. It's crazy. It's a temporary variable, declared at the top, initialized in the middle, used down the bottom. Yeah! I hate temporary variables. Our refactoring is going to be to get rid of it altogether. Now before we can talk about that refactoring, I have to remind you a little bit about 1927. In COM 1927, we spent a fair bit of time talking about complexity and the speed of algorithms and the correctness of programs and the computational and the time complexity of programs and the memory complexity of programs. And we also had lots of times when I just chatted at you about various things. And one of the things I would have ranted a fair, or I did rant a fair bit about, hopefully you've remembered, is optimization. Remember when we were trying to make our Busy Beaver really fast? And we were talking about speed. Do you remember my tips about speed? What were my speed tips? Anyone summarise the most important thing that I said about speed? Yes, you've got to get the right algorithm. Yeah. I mean, in the wrong algorithm is just the end of the world.
When you're optimizing, so you pick things that will give you the most benefit.
Yes. When you optimize, it's not an equal society. When you optimize, don't put an equal amount of time in every little optimization you do, because some of the optimizations will save you a microsecond, and some of them will save you a year. Only bother putting time in the year one. Only when you've finished all the year ones Is it worth spending time on anything that's going to save you less than a year? And only when you've saved time on all the ones that save a month is it worth even looking at the ones that are going to save you a day. And only when you've fooled around with the ones that are saving you a day is it worth, and there's no more of those to do, is it worth thinking about minutes. And it's probably never ever worth thinking about the ones that save you a few milliseconds over the life of the program. That's just a complete waste of time. So the trick is not to optimise with everything you do, not to always be writing code and optimising as you go in your head, because it will turn out that most of that stuff that you're doing is irrelevant. And I've already done this in my chess program. I found myself doing it annoyingly. Has everyone handed in their chess programs now? I was writing mine one, and I had something to represent a square on the board. And I realised, and I needed this to access various functions. And I realised that if every time I needed to access a square, I created a new square object. Over the life of the program, as I'm doing my lots of looking ahead into the future, I'll be creating very, very, very many squares and then destroying them and throwing them away. And when I compare the squares, I just compare their two coordinates to see if two squares are equal, because I represent a square by two coordinates, because I can't compare the pointers, the references to the objects, because I may well have two different squares with the same coordinates. I might have created, if I want to talk about square 3, 4, I'll go new square 3, 4, and then I might have a square 3, 4 in a list somewhere, but it's talking about the same square, but it might have been created at a different time. And I worried about that a lot. I thought, oh, that's really inefficient. So what I did was, in my board, I created a cache of squares, one per square on the chessboard. And every time I wanted a square, I asked the board to give me this canonical square back. So there was only ever one square for every square. And that meant to compare two squares, I could just compare references. This added enormous complexity to my program. And afterwards I thought, why did I even do that? I was prematurely optimizing. You write your code first, you make it beautiful and clear, and then you find out where the bottlenecks are, and then and only then, if it's unacceptable, do you do anything about it. And you only bother about the bottlenecks that are the biggest, that are the narrowest neck, the biggest bottle to neck ratio. Okay? So me just doing that was just adding crud to my code, and adding so much complexity. I've kept it for you to laugh at. I will release the different versions of it, so you can all laugh. So the temporary variable here, we're not going to keep. We're going to throw it away. The thing that's going to let us do this is, when is it written to? Can you see when is it written to? It's created, written to, and it's given an irrelevant initial value here, you know what I think of that? It's written to, then it's read twice. So it's only written to once. In which case, what am I going to suggest we do? What's Martin Fowler going to suggest we do? Sorry.
Do you call it both times?
Yes. Replace temporary variables with a query. Optimization number 3. So take each get charge and stick it here and stick it here. Delete this line and delete this line. Now we call that twice in every loop instead of once, which is terribly inefficient. Do we care? No, we don't give a damn. We will only care if at the end our program runs too slow, and then we'll do a lot of thinking to work out what we're going to take to speed it up. And I can guarantee that if this is something that's used for printing out statements, it's very unlikely that this code is run very often, probably just once a day. And the number of statements printed out, presumably, is at most the number of videos we've got in the library.
Should it also be the responsibility of the rental to optimize it?
Yeah, yes, maybe the rental could cache it or something like that. Yes, that's right. Theo's saying any optimization, if we're going to do it, maybe we can delegate that down to the rental object anyway. And it can remember, I've already calculated this once, I don't need to calculate it again, because nothing's changed since the last time I calculated it.
You don't want the classes that are using it to have to think about how they're implementing.
Yes, generally, yes, that's right. This is called the uniform access principle. You don't want the classes that are using the methods, or that are accessing the other classes. I'm accessing you to get some stuff. I don't want to think about how you're doing it, or how you're storing it, or how you're representing it, or any of your internal implementation at all. I just want you to give me the stuff. And if there's optimization to be done, well then, maybe that's the right spot to do it. Maybe it isn't. But certainly that's a good general principle, that let everyone worry about themselves rather than. So This is the next optimization to get rid of the temporary variable. You seem a weird thing to do. Can you see the two bulbs there? Okay, all right, now we might, just everyone seems to be falling asleep, so we might take a little pause. Let me just startle you with lights on. Oh, no! Oh, man! I did have something I wanted to show. All right, I'm going to talk about the class reps. Your project that you're all working on, at the end of, we're now in our second Platipiad. Our first Platipiad was learning Java. We've now sort of learned all the Java we need to know. There's a couple of little things that we'll see over the next couple of weeks, but we've climbed that hill. We're now in the position of knowing all the Java we're going to need to use, and now we're in the position of, oh, okay, using it to do cool things. Second Platipiad is the Platipiad of getting ready for the project. It's really the project Platipiad. During these 4 weeks, you guys will be inventing the tests that your code has to pass. From the end of the second Platipiad on, you have no more say. At the end of the second Platipiad, the tests you propose are the ones we're going to have. And if we, the tutors, look at them and decide those tests are not sufficiently testy, we'll throw them away and write our own, and you'll just be given them as soon as we write them at the last minute. But we'll give them to you as soon as we can. We won't be deliberately bad, but it's much better for you to know as early in the process as possible what the tests are. So you have to come up with your own tests. And as you saw, do you remember in the first lecture I said, guys, you've got to be with a project partner, and you're going to be doing all your project programming with this partner, and partner work is really hard to do, and the quality of the pairing that we managed to do for you for the project will be really instrumental on your pleasure in this course, and it will be just really nice for you to have a good partner, but I'm not sure the best way of coming out with a partner is what I said. We tried all sorts of things last year and it wasn't clear which work we did. So I thought I'd ask you guys how we should allocate the partners. And it was just like deafening silence. Didn't say my name. I don't have to say anything. Does anyone have an idea? And I think, is it Takashi? Yeah. You were the only one that had a suggestion. You had this awesome suggestion, but it was too hard to implement, some sort of auction or something like that. But you were thinking about it, and you had a good idea and you spoke up. But no one else had any ideas, so we didn't decide anything. So eventually I said, oh, well, we'll let your tutors decide then how to do it, and we'll have some exercise where you can do your first presentation, and they'll see who puts a lot of effort in, who doesn't. And they'll look at everyone's marks from last year, and they'll try and pair people up with people of equal enthusiasm based on those 2 clues they've got. But I just want you to notice that you did in that first lecture have the chance to suggest whatever method would have been better than that default method we ended up with. But it's very hard in a large group of people to ever get any sort of agreement at all. Now, because we need you guys to come up with a set of tests and everyone's going to be tested on the test, we need to have agreement. So instead of having direct democracy, where everyone got a vote and everyone's opinion was accounted, like the Greeks had in their big assembly, we switched to something called representative democracy, where you guys get a representative, and those representatives act on your behalf. So every tube has an hopefully elected, possibly appointed if no one wanted to vote, and elect a representative to represent that tube in working out how the tests go. Now those representatives are hopefully very soon going to be able to give you the interfaces that you will need to program to. And then I'm hoping over then a couple of weeks, you guys will suggest tests for those interfaces, and by the end of phase 2, particularly at 2, we'll have a uniform set. And so you'll be hopefully speaking to your representatives each week. I know Kitten did a fantastic presentation in his tube explaining the interfaces so far. That was really good, and hopefully the other reps are doing the same sort of thing, telling you how it works. But of course the reps, like the ancient Greeks, are just serving in public office to help you guys. They're not getting any credit for it, just like the ancient Greeks. In ancient Greeks, public servants weren't paid, they were just appointed. It was like a lotto. They just drew them out of a ballot. Oh, you're the king this year. You're the toilet cleaner. You've got to look after the streets as well as looking after your farm and things like that. And everyone was given a job, and every year it was just everyone was given. And it was this idea of citizenship, that part of being a citizen was you did your job and did the best you could and so on. And everyone had a chance at doing every job, and it was really, really cool. So your reps are doing this great job out of a sense of citizenship, and I'm hoping their citizenship marks will reward this, but it doesn't mean you're not doing anything, because you're then hopefully going to support them and cut them a whole lot of slack in other things, and do lots of test groups. Now there are problems with a representative form of democracy. In some ways, although it's easy to come to decisions, it's not as good a form of democracy, presumably you can see as complete correct democracy, because it's harder to capture the full will of the people. And if you take the extreme of tyranny, where there's just one person, it's very easy to come to decisions, but you have the least representative of all of them. And so there's a famous, and the reason I'm saying all this is because there's a very famous speech by a Canadian politician about representative government. And I thought we could go into our break playing this little speech. And it's called Mouseland. Does anyone know Mouseland? Mouseland. Oh, no, it doesn't. There's one you control below.
I would like to tell you a story. It's the story of a place called Mouseland. And this is where all the little mice lived and played, were born and died, and where they lived much the same as you and I do. They even had a parliament. And every 4 years they held an election, used to walk down to the polls and cast their ballots. Some of them even got a ride to the polls. And they got a ride for the next 4 years afterwards, too. Just like you and me. And every time on election day, all the little mice used to go to the ballot box and they used to elect a government. A government made up of big, fat, black cats. Now, if you think it's strange that mice should elect a government made up of cats, you just look at the history of Canada. And maybe you'll see they weren't any stupider than we are. Now, I'm not saying anything against the cats. They were nice fellows. They conducted their government with dignity. They passed good laws. That is, laws that were good for cats. But the laws that are good for cats aren't very good for mice. One of the laws said that mouse holes had to be big enough so that a cat could get his paw in. Another law said that mice could only travel at certain speeds so that a cat could get his breakfast without too much effort. All of the laws were good laws for cats. But oh, they were hard on the mice. And life was getting harder and harder. And when the mice couldn't take it anymore, they decided something had to be done about it. So they went en masse to the polls and they voted the black cats out. They put in the white cats. And still, nothing changed.
This is an illegal gathering, and we're shutting it down now. Everybody out!
We have a right to a meeting.
Not without a permit. Bylaw was passed just this morning.
I ripped up. I showed you the wrong one. This is a stupid movie with people laughing. There's actually a recording of the actual politician giving the speech. It's a fantastic speech. But just to summarise, he talks and talks about how they had appointed the black cats, and the black cats didn't represent them very well, and they eventually voted them out, and they voted in the white cats. And then the white cats didn't look after them very well, and it was really tough too. So they voted the white cats out, and they voted the black cats in. And it's very good. So you should check it out. But anyway, it's a speech a long ago by a great Canadian politician. But the problem with representative government here is... Yeah, they're only representatives, so if your representative isn't representing you, you're in trouble. All right, but I'm not saying anything about your representatives who appear to be completely awesome, but I'm just pointing out to you the slight step away from direct democracy we made when we moved to representative government. But we still haven't got to total tyranny, which is what will happen in your next course, you know. Right, so take a little break now, guys.